Yeah.
All right. Good afternoon. Let's continue kinematics. So yesterday we finished function generation for the slider crank, and on Monday we talked about function generation, kinematic synthesis for function generation, and four-bar mechanism. So what we learned for four-bar mechanism. We wanted to design or synthesize a four-bar mechanism to generate a desired function or desired correlation between theta and phi. For example, if theta 1, 2 is (30°), we would like to get phi 1, 2 equals to 90. And then theta 1, 2 is 45°, phi 1, 3 be 120. So we talked about the method. We are going to end up to the 6x6 system of equations. But the number of unknowns that we could count are 8. But since we have 6 equations, we had to pick 2 of them as the free choices. And we pick beta 1, 2 and beta 1, 3 as free choices. But you can pick theta 1 and phi 1, different free choice. And solve for the other 6 unknowns. You might ask, why do we need to pick the different free choices? If you look at this example, this is the ladder that we would like to design a four-bar mechanism. One is ground. There is one joint connected to the ground. This is another joint that we would like to have it here, and one link here, second link, and fourth link number 4. We would like to design a four-bar mechanism such that it can open the mechanism or the ladder, and it goes through. If this is the input angle, then theta 1, 2 is 24°. We would like the ladder is opening by angle of 30°, and when it rotates by 40°, we would like the ladder opens by 30 here, 50 here, 80°. So this is what we want to know. So we would like to design this mechanism. You might say we can design this with the free choices of beta 1, 2 and beta 1, 3. If you do that, you can find A, B, C, and D is 1, and also you will find theta 1 and phi 1. Theta 1 is the angle of this link at the starting point, and phi 1 is the angle of the mechanism at the starting point. But what we want is, at the starting position, we would like to have phi 1 equals to 180°. So the phi 1 that we want to get is 180°. And by picking beta 1, 2 and beta 1, 3, you might get different value for phi 1. One way is we can try different beta 1 2 and beta 1 3 to get phi 1 equals to 180, but it's difficult approach. So what we are going to do, we are going to introduce the new method. It's going to do the same things. It's going to do the kinematic synthesis for function generation, solving this problem. But instead of picking beta 1 2 and beta 1 3 as the free choices, we are picking free choice as theta 1 and phi 1. So we call it Fredeunstein method, and we will see how it works. For this example, I pick phi 1 equals to 180 and theta 1 any angle which is desirable for the design. 20, 25, it depends on your constraints. So this is why we introduced the new method. So let's see how this method is set up. So we'll start from 4-bar mechanism. This is a 4-bar mechanism that we have. The loop closure equation is going to be A cosine of theta plus B cosine of beta equals to D, which is 1, plus C cosine of phi. For the x, for the y, just change cosine to sine. D doesn't have any y component. We are going to get C sine of phi. We have seen this on motion analysis or displacement analysis for a 4-bar mechanism. And that problem, we are given with theta, we are solving for beta and phi, if you remember. What we did, we tried to get rid of either beta or phi and solve for the other one, and back to these two equations to solve for example, beta. So if you want to get rid of beta, you move other terms to the right side, a square, you will get p square cosine square of beta equals to 1 plus cosine of phi minus a cosine of beta, theta square, and b square sine square of beta equals to c sine of phi minus a sine of theta square. If you square and add them up, you will get b square cosine square of beta plus sine square of beta equals to this square plus this, which is this plus this. This side is going to be b square. The right hand side was plus c sine of phi minus a sine of theta square. So this is what we did in 4-bar mechanism. The same thing. Theta 2 is our theta. Theta 3 is the beta, and theta 4 is phi. So what we did the same thing. A square times this equals to the right hand side. On next slide, I'm going to show you how we simplify this. Since I don't want to rewrite them again, I'm just going to the final equation, which was Fredeunstein equation. In Fredeunstein equation, we got k1 cosine of theta 4 minus k2 cosine of theta 2 plus k3 equals to this right hand side, cosine of theta 2 times cosine of theta 4 plus sine of theta 2 sine of theta 4. If you look at this, it's going to be equals to cosine of theta 4 minus theta 2. If you expand this, you will get cosine of theta 4 or cosine of theta 2 times cosine of theta 4 plus sine. So it's going to be, if you expand this, you will get the right hand side. So I'm going to rewrite this as cosine of theta 2 or theta 4 minus the other one. Similarly, theta 4 is this guy, so I can write k1 cosine of phi minus k2 theta 2 is going to be theta plus K3 equals to cosine of theta 2 theta minus 2. So it's going to be the equation that we are going to use in this method. And if you remember, K1 was D over A. Since D is 1, it's going to be 1 over A. K2 is D over C, which is 1 over C. And K3 was A squared plus C squared plus D squared is 1 minus P squared dividing by 2AC. So this method is based on this Fredeunstein equation. Now, it's a 3 precision points. This equation should valid for the first precision point, second precision point, and third precision point. So for the first one, angles are cosine of phi1, K2 cosine of theta 1 plus K3 equals to cosine of theta 1 minus phi1. Second equation, K1 cosine of phi2 minus K2 cosine of theta 2 plus K3 theta 2 minus phi2, and K1 cosine of phi3 cosine of theta 3 theta 3 minus phi3. You will get 3 equations which should be valid for all 3 precision points. 3 precision points means I can write this equation 3 times. And these 3 equations, if you look at this, you will see K1, K2, K3 as unknown. We are solving for K1, K2, K3. What would be the phi1 and T1, theta 1? You pick as the free choices. So these 2 are not known. So theta 1 minus phi1 is known. What would be phi2? Look at this. Phi2 is phi1 plus phi1 2. Whatever you pick for phi1, just add it to the given data, you will get phi2. Similarly for theta 2. Theta 1, 2, which is 30 plus theta 1, which is free choices. For phi3, you have phi1, 3, you can find phi3 and theta 3. So everything except K1 and K2 and K3 are now, you can solve for K1, K2, and K3. How can we solve this? The unknowns are K1, K2, K3. These 3 terms they have K1, K2, K3. I have the variables or unknowns here. What is the coefficient of K1? It's cosine of phi1. What is the coefficient of K2? Negative cosine of theta 1. And coefficient of K3 is 1. Right hand side is the cosine of theta 1 or phi1 minus the other one. Second row, cosine of phi2 minus cosine of theta 2, 1. Cosine of phi3 minus cosine of theta 3, 1 cosine of theta 2 minus phi 2. Cosine of theta 3 minus phi 3. Solve this system of equation 3 by 3 and get value for K1, K2, K3. But we are looking for A, B, C, and D is 1. Back to this, after you find K1, A would be 1 over K1. B would be 1 over C is 1 over K2, and D you solve for B. 2AC times K3, it's gonna be just A squared plus C squared plus 1 minus 2AC K3. It's gonna be B squared. So B is gonna be, I just try to solve for B. I mean, you calculated A, you have C, 1, 2AC, and K3 is coming from this system of equation, solve for B. I just have B value over there. So now you have A, B, C. What are the theta 1 and phi 1? Theta 1, phi 1. It's calculation wise, it's much easier than this because here we had 6 equations with 6 unknowns. Any question on this? Those problems, both problems, they are solving for A, B, C, and the input angles. But here you need the free choices are beta 1, 2, and beta 1, 3. In Fredeunstein method, the free choices are theta 1 and phi 1. Any question? All right. So let's look at. We did this problem we solved this problem with the first method. We would like to design a forward mechanism to generate this desired function, theta 1 to 30, phi 1 to 90, and when theta 1 3 is 45, we would like phi 1 3 equals to 120. And we picked the free choices for that. I believe it was beta 1 to 25, beta 1 to 45. Here I pick free choices for 40 and 60 for theta 1 and phi 1. So if theta 1 is 40, and phi 1 is 60, theta 2 can be calculated by adding 30 to 40, and phi 2 is going to be 90 plus 60, which is 70 and 150. Similarly, theta 3 equals to 85, which is 40 plus 45, and phi 3 equals to phi 1 3 plus phi 1, which is 60. This is all you need to solve this system of equation. This is matrix A. Cosine of phi 1, which is 60, negative cosine of theta 1, which is 40, and 1 second row 150, 70, and 1, 180, 85, and 1. So this is A, which you can get the matrix A, and vector B. Right side, cosine degree of theta 1 is 40, phi 1 is 60, or you can write 60 minus 40, because you know that cosine of theta equals to cosine of negative theta. So don't worry about the orders. Second row, theta 2 minus phi 2, just 70 minus 150, and 85 minus 180. And then A, backslash B, you will get K1, K2, and K3 in order. K1 is 0.29 or 6. K2 is negative 0.87 or 6. And K3 is 0.1275. So you have K1, you can find A. Just 1 over K1, it's going to be 1 over 0.29. Back to the slides. A is going to be 3.44. C, we got K2 negative. So 1 over C is going to be negative 1.15. But the length cannot be negative. I'll show you how can we handle this. And if you plug in A and C, A 3.44 and C as a negative 1.15, don't change the sign when you want to use to calculate B. B squared plus C squared plus 1, it's a B squared. A squared, sorry. A squared plus C squared plus 1 minus 2ACK3, you will find B equals to 3.89. So now, if you want to draw the mechanism at the first precision point, where A is 3.44, theta 1 is 40. At the angle of 40, go by by 3.44. D is 1, so D is here, O2, O4. If I want to draw C, the phi 1 is 60, but the value that I got for C is negative. What I need to do, I just need to rotate link C by angle of 180. So if this is C, just rotate it by the angle of 180 and draw the C in the other way. So the C is 1.15, it's going to be somewhere here. So it's going to be, if this is point A, point B, it's going to be point B. This is going to be 1.15 and connect these two. .40°, this is 60°. Instead of going in 60°, just go in the opposite direction by the length of positive 150. This is how you can handle the negative value for A and C. For B, for sure, you will get positive because it's a square root. But for A or C, you might get a negative sign. If you got negative sign, it means you, instead of going in this direction, you should go in the opposite direction by the angle of 180. Second position, you just add theta 1 to 240, you will get 70 degree, just like this, and 30 second, which is going to give us angle of P1, P3 side. Any question on this? It's an important method. If you have time, we will work on one example to show you what would be, how can we use this method and in applicable mechanism. So if I want to summarize this method, in Fredeunstein method we pick theta 1 and phi1 as free choice. If you pick this value, you can simplify theta 2, phi2, theta 3, and phi3 by knowing these two, because this is given. Then you can set up this system of equation and solve for k1, k2, and k3 and find A, B, and C. And D is 1, and you can sketch the mechanism in 3 precision points. Again, if C or A are negative, just rotate the mechanism, that link by the angle of 180 degrees. All right, let's look at the synthesis of 6-bar mechanism. It's a 6-bar mechanism. 1 is ground, 2, 3, 1 tenor links, number 4, 5, and 6. And we are given with this given data. We would like to have theta 1 to 30, and gamma 1 2 is the orientation of this link, equals to 60, and phi 1 2 at the same time 55. Means when I rotate this link, the input link, at the starting point by the angle of 30, I would like this tenor link is rotating by 60 degrees, and this output link is rotating by 55. And when I rotate this by 45 degrees, I would like to rotate this coupler, this tenor links by 90 degrees, and this should be rotated by 120 degrees. I can change this problem to 2 4-bar mechanism. Just look at this mechanism, A, B, C, D. It's a 4-bar mechanism with this given data. Theta 1 2 is 30, gamma 1 2 we would like to have 60. Theta 1 3 is 45, gamma 1 3 is 90. So just looking at the first 4-bar mechanism, you can design or you can size A, B, and C such that it generates this desired function. You can either use Fredeunstein method or the other method that we covered on Monday class, depending on the problem, and size A, B, C, and this. This is one. After sizing A, B, and C, you also if we use the first method, we find theta 1 and phi 1. And gamma 1. Theta 1 and gamma 1. If we use the second method, we free choices are theta 1 and phi 1 and gamma 1, sorry. In any way, gamma at the starting points are given. Then we look at the second mechanism, which is then we size A, B, C, D, E, F, G, and this one is going to be 1. So we size this guy because we are given with this set of data. If the gamma 1, 2, if this guy is 60, we would like the output is 55. If gamma 1, 2 is 90, we would like to have phi 1, 3 equals to 120. So we can size E, F, G, and this one is 1 again. So this is how you can do the kinematic synthesis for 6-link mechanism. And the application for that is when I showed you on first day that we started kinematic synthesis. One example that I showed you, designing a mechanism for this carburetor mechanism. This is a gas pedal or accelerator pedal. We would like, when we push it by angle of 15, we would like gamma 1 to this middle link or bell crank is rotating by 10.5. And at the same time, we would like the carburetor is opening by 20 degrees. And second desired motion or function is when you want to speed up the car, you push more by pushing to 25 degrees. This one we would like to open by 17 degrees. And the carburetor should be open by 40 degrees. So this is exactly the same as this mechanism. We designed a 6-bar mechanism, combination of 2 4-bar, which they have been connected together through this terminal link. So one group can do this if they want to work on the function generation and design a mechanism such that it generates this desired function, which is applicable for the carburetor mechanism. I already posted the sample project. One of them is this one. So if any group is interested, we can talk about the angles, but if you pick that one, you should put some pointer that I can make sure that it generates the desired function. Because just think, how can I make sure that by pushing this by 15 degrees, the middle crank is rotating by 10.5 and the carburetor is opening by 20 degrees. Somehow you should add some pointer to the mechanism which shows the motion of the mechanism. Any question on this? All right. So let me start working on the example which shows the application of the Fredeunstein, where can we how can we use this method in some specific application. When we were talking about the different mechanism with function generation, we talked about this metering device. So inside this black box, we are going to have a 4-bar mechanism. One is ground, 2, 3 that we don't see inside, I mean it's kind of inside, and link number 4. And here we have X, and right here we have Y. We would like, when this arrow is at the X one, the other arrow is showing us Y one. And when it goes to the, for example, X2, this arrow will be at Y2. How can we design a mechanism such that it generates this function? It's a function generation because we are given with a correlation between the input link and the output link. So it's kind of function generation. And I showed you one mechanism which could generate a desired function ln of x we would like to design a 4-bar mechanism such that if the input link is showing us X, the output link is showing us ln of X. So this is the input link, and we label this goes from 1 to 10. We would like, when this arrow is at x equals to 1, the output link, which is this guy, link number 4, is showing us the ln of 1, which is 0. And when it goes to 2, it's showing us the ln of 2. So it's kind of metering device that you can give someone, and it can change the x and get the value for ln of x. So when it goes to 2, it's rotating to ln of 2, and when it goes to the 3, it shows the ln of 3, and so on and so on. It's kind of function generation, but we are given with the correlation between x and y. What would be the correlation between x and y? Y is ln of x. So we want to generate this correlation. But in typical problem that we solve here, we usually given by correlation between angle, input angle, which is theta, and output angle, which is phi. So we know if we are given with the correlation between theta and phi, we know how to solve this problem with the Fredeunstein method or the first method that we covered in the class. But right now we are given with the correlation between x and y. What we are going to do, we are going to find a correlation between theta and x. As you see, theta and x, they have a correlation. So when theta is changing, x also is changing in a specific pattern. And also find the correlation between phi and y. And then instead of dealing between x and y that we have the correlation, we are dealing with the correlation between theta and phi and synthesis or design the mechanism. This is the idea. So let me write the example problem, but I'm gonna start working on that on Monday. So we would like synthesis of 4-bar mechanism by using Fredeunstein to generate the function y equals to sine of x. So here we have y equals to ln of x. Now I would like to have y equals to sine of x. When I label x here, I would like to get sine of x on output link. For angle of x between 0 and 90. So the range of x, it goes from 0 to 90. So I'm going to label this from 0 to 90, and not more than that. This is what I want to generate. And the range of input angle is 120 degrees. What do I mean? If this is x goes from 0 to 90. For that range, I would like the input link is moving from a starting point, whatever is that, the starting angle, which is theta 1, all the way to angle of 120 plus theta 1. So the range of motion we would like to have 120 degrees. It means delta theta should be 120 degrees. And range of output link is the phi we would like to have 60. So when the input link is rotating by the 120 degree, we would like the output link it just covers 60 degree. So this one it's starting from 0 all the way to 90 degree. This one should start from sine of x, sine of 0, all the way to sine of 90 degree, which is 1. We would like to design something like this. But we would like to have these 3 precision points. at x equals to 6 degree, x equals to 45 degree, and x equals to 84 degree, we would like to get exactly same value for the sine of that. Because after you design that, you might have some error between the desired design, which is y equals to sine of x, and the actual design. But we don't want to have any error at these 3 points. 6 degree, when this is at 6, for example at 6, this is 6, we would like this guy is showing us sine of 6. Sine of 6 should be shown. And when it goes to the angle of 45, we would like to see exactly sine of 45 in y. And also in angle of 84. This 3 precision point, it's gonna set by u. So in this example, I set these 3 precision points. So this is the problem. As you see, we are given with the correlation between y and x, not between theta and phi. So what I'm gonna do, I'm gonna connect x somehow to theta and y to phi. And I have the correlation between x and y, meaning that I can have the correlation between theta and phi, then I can solve the problem with the Fredeunstein method. We will work on this example on Monday.